So now let's move on to dimension and dimension analysis. In this part of the lecture, we want to consider the dimension of a quantity. So here the dimension of a quantity refers to the type of the base unit or the base quantity that makes it up. Take for example, let's look at area. When we look at area could be pi r squared or 1/2 base times height. These two formulas describes area, but can we really verify that these two formulas are correct? For us to do that, we know that area has a unit meter squared. So whatever formula that is used to describe area must have a final unit meter squared. And here we need dimension analysis to do that. So when you say area is equals to pi r squared, our base unit that makes it up is length times length, and that is meter squared. So which means that this is correct. And when you say half base times height, half is a constant just like pi is a constant. Base is in meters, height is in meter, which means meter squared. So those two formulas are correct. And what we have just done now is called dimension analysis. So what we are saying here is that the formula for a certain quantity may not necessarily be the same in certain instances, but it is expected that their dimension stays the same. Here the word dimension means that the base quantity that was used to formulate that physical quantity must remain the same. Here we have a table showing us different physical quantities and their dimensions. Just the same way I mentioned, area, length times breadth, and the dimension is length squared. So we represent the dimension in square bracket, and the dimension formula is m raised to power 0 L squared T raised to power 0. Our volume is in L cube. Our mass density, which is given as the ratio between mass and volume, is given as m to represent our base quantity mass divided by the volume, which is from the base unit L cube. There's something you should take note here. We can write m divided by L raised to power 3 or m times L raised to power minus 3, all the same. Okay? Then we have power, which is equals to work divided by time. Our work has the base unit is ml squared t squared. Don't forget that your work is defined as force times distance. So when you put your force times distance, your force is ml t squared as shown here. Let's look at work. Our work is given as force times distance, and that is mlt raised to power minus 2 times your length. So your length here, L, is from your distance, and your force here is ml t raised to power minus 2. And here we define our force as ml t raised to power minus 2. Last time we said that mass times acceleration gives our force from second Newton law. You can go through this table in your coursework. Let's consider a problem. Here in this problem, we have two formulas that is proposed or is written to be correct for a period. Here a period in physics means the number of the time it takes for a complete oscillation. We have a topic which is called oscillation, which we shall discuss in our future video. For now, we take period t to be given as 2 pi square root of L divided by G, or T is equals to 2 pi square root of G divided by L. We know that our period has a unit seconds. So we want to know which of these two equations or two formula is correct to represent period. So let's work it out and verify ourselves using dimension analysis. So let's consider the first formula. Let's check if the first formula is correct. So what do? We write T is equals to 2 pi square root of L over G. Don't forget that our base quantity is in mass, length, time, luminosity, and so on. But for this case, we just concentrate on the three base quantity. Now let's look at this. We have our 2 pi as a constant, so we are not bothered about that. We have our square root. Our length is in L from our base quantity, and our G is our acceleration due to gravity, and our acceleration due to gravity has been given to us, which is G is equals to L over T squared. So we just substitute the base quantity for G, which is going to be L divided by T squared. And if we do this simple algebra, what do we have? We have L divided, by L over T squared. So which is the same as square root of L multiplied by T squared over L. So we can strike out L, and we are left with square root of T squared. So our final answer becomes T is equals to T, which we know that T is in seconds, but T here on the left hand side represents our period whose base quantity is T. So this is correct. So we know that this is correct, but want to check whether the second relation for period is as well correct. So what do? We write T is equals to 2 pi square root of G to L. So in terms of the base quantity, we know that 2 pi is a constant, so we have our square root, and G is already given in the question as L over T squared. Then we have our division here, and we have our L. So if we do this, we have our square root, and we have our L to T squared. If we put our divided by L, it's the same as 1 over L, right? So if this cancels out, we are left with square root of 1 over T squared. And square root of 1 over T squared is the same thing as 1 over T. This is not correct. T is not equals to 1 over T. So for that reason, this second formula is not correct. So you can see the advantage of using dimension analysis to probe the relationship between physical relationship, or to check for the validity of equation. We also have here show on the basis, another example, show on the basis of dimension analysis that the relation between this is your eta, is equals to P times R raised to power 4 is correct. Or let me put it as eta is equals to P raised to power 4 divided by your delta VL, where your V is defined as your volume per seconds. So we want to determine if this relation is valid, and we define this constant here as coefficient of viscosity. Again, to remind you, we have a topic that deals with fluid, and we shall be talking more about viscosity in our future video. Our goal here is to check if the relation that describes our coefficient of viscosity is correct. So let's start. We start with the right hand side, which is our pressure, and we know that pressure P is given as force over area. So now our force, as we defined earlier, is defined as product of m, which is our mass, times acceleration divided by area. So if we put our pressure in terms of dimension analysis, becomes m to represent the mass, our a, which we have done earlier, whether it's acceleration due to gravity or acceleration, is given as L t minus 2, or L divided by t squared. So here we can write ml t raised to power minus 2 divided by our area, which is L squared. If we do this, we have our pressure to be m L t minus 2 raised to power L minus 2. And when you have this, your final answer will be m. If you look at indices, L is the same. So this is going to be plus 1 minus 2 becomes ml minus 1 t minus 2. If this is clear, then we substitute that for our pressure. Okay, and that's where we get this, which is ml minus 1 t minus 2 that we just worked out. And this represents our pressure. Then the rest is R, which is in meter, and we have it as L raised to power 4. Divided, we have our division here. Dimension of volume is given in the question as volume per time. And our volume is L cube, and time is 10 raised to power minus 1, since they said per time. So when you have 1 over t is the same thing as t minus 1. Then we have our L here, and that is our L. So we can resolve this using simple indices. So we have our mass here, we have our mass here, we have L raised to power minus 1 and L raised to power 4. From indices becomes L raised to power minus 1 and L raised to power 4 becomes L raised to power minus 1 plus 4, which is L raised to power 3. Okay, if that is clear, then we can get this L minus 1 L raised to power 4 become L3. We still have our t raised to power minus 2, then I have our division here. Now when we have L raised to power 3 and L raised to power 1, that becomes L raised to power 4, and we still have our time raised to power minus 1. If we take our time up here, becomes t positive. Okay, so it becomes t positive, and that becomes t raised to power minus 1. And our L, if we take it up, becomes L raised to power minus 4. And L raised to power 3 minus 4 becomes minus 1. So everything is accounted for, and this is our base quantity that makes up our coefficient of viscosity. The next goal is to now consider what is the known formula for our coefficient of viscosity, which we shall consider in the next slide. So we know that this is the known formula for our coefficient of viscosity, from F is equals to this one, tau A V then L. So now we can have our coefficient of viscosity. We have our force defined. This is our force. Then we have our L. This is my L. Then our area is L squared. Our V here is velocity. And velocity is V equals to L over T, which is the same thing as LT minus 1. We have LT minus 1. Everything is accounted for. Then if we take all our denominator to numerator, so let's start with our L. Here we have numerator, we have L squared. If we take our L raised to power 3 becomes L minus 3, and that becomes L minus 1. We have our M. Let's look at our T at the numerator, so we can cancel this. At the numerator we have T minus 2. If we take our T here to the numerator, our T from the numerator to the numerator, we have T positive 1. And from indices, this becomes T minus 1. So we have T minus 1. So we can see that what we worked out on the left hand side equals to right hand side. So therefore, the relation we are asked to check is correct. Okay? So we can summarize what we've learned so far. We've been able to understand the base quantities in the SI units, which are length, time, electric current, mass, temperature, substance, which is in mole, and luminosity. We also understand our prefix, and we also learn how we can convert from one physical system to another using chain link method. We've also learned how we derive other physical quantities from our base quantities, and lastly, we were able to apply dimension analysis to problem involving approximate relationship. So this brings us to the end of this video. In our next video, we shall be talking about scalar and vector quantities. Thank you, and see you in the next video.